Hello and welcome to this session on linear regression. In this session, you will understand what linear regression is all about. Here we have a scatter plot. On the x-axis, we see study hours representing the amount of time students spent studying. On the y-axis, we have test scores showing how well they performed in an exam. Each dot on this plot represents a student. As you might notice, there seems to be a pattern. More specifically, a general trend where more study hours lead to higher test scores. But how can we quantify this relationship? How can we use it to make predictions for new data? That's exactly where linear regression comes into play, and we'll be learning how it works step by step in this course. Before moving on, let's take a moment to understand what makes a prediction bad versus what makes it good. We will explore an important concept called residual error. Here we see just one actual data point represented by a blue dot and a predicted value illustrated by a yellow dot. Notice the difference between the two. The distance between the actual data point and the predicted point is called the residual error. Initially, you can see that the predicted value is far from the actual value. This means the residual error is high. But the better prediction is one where the yellow dot gets closer to the blue dot. In simpler terms, a good prediction minimizes the residual error. Now, let's switch back to our main example, where we'll introduce a critical part of linear regression. The formula for the line of best fit is given. Here, y hat represents the predicted value, a is the slope, b is the intercept, and x is our input variable, that is study hours in this case. Initially, the line is horizontal. When the line is horizontal, the slope is 0, meaning there's no upward or downward tilt. As you can see, the change in x does not affect the overall prediction outcome, since the prediction here depends on the intercept, as the slope is 0. Let's change the intercept slightly. As we adjust the intercept, the change in x still does not affect the overall outcome, as the slope is 0. To illustrate how the slope affects the line, let's focus on the rightmost side of the line. As we tilt this side upward or downward, you'll notice the slope increases or decreases, which directly impacts the predicted output for a given x. Before proceeding, please note that we are now displaying the output for x with a value of 13. Now let's move to the leftmost side of the line to adjust the intercept. As we change the intercept, you'll see the entire line shifts up or down. It's important to note that the slope remains unaffected. Slope and intercept are independent of each other. Changing one doesn't impact the other. Now let's return to the main example to see how the line evolves as the machine learning algorithm works to minimize the error. Initially, we start with a line position near the bottom of the plot with an intercept of 1.4. To calculate the residual error for all predicted values, we use the residual sum of squares formula. This formula measures the total square difference between the actual data points and the predicted values. A smaller RSS indicates a better fit of the line to the data. Previously, we discussed how the line formula works and the steps involved in adjusting the slope and intercept. We will skip showing the calculations for the line formula and assume they are being performed in the background. In the first step, the RSS is quite high at 24.68, which indicates poor predictions. To improve this, the algorithm begins adjusting the slope and intercept. It tries different combinations, recalculating the RSS at each step. The goal is to find a slope and intercept that minimize the RSS, thereby creating the best fitting line for the data. After the initial prediction, the algorithm continues to adjust the line to minimize the error further. In this step, the intercept remains the same, but the slope is adjusted just a little bit. Notice that when we update the slope, the line starts moving upward or downward slightly based on the new slope value. This change is small, but it's aimed at improving the fit to the data. After recalculating the new predictions using the updated slope, the RSS is now reduced to 17.87, which is better than the initial value of 24.68, but it's still considered high. Now in this step we keep the slope the same, but we change the intercept considerably. When we adjust the intercept, the line shifts vertically, which results in new predicted values for all the data points. After making this adjustment, the RSS now reduces to 5.75, which is a huge improvement from the previous value of 17.87. While this is a much better fit, the machine learning algorithm can still continue to adjust the line to further minimize the error. And finally, both the intercept and slope are adjusted together, resulting in a significant reduction in the residual sum of squares to 1.86. Machine learning stops the fitting process when it reaches the minimum RSS or when further adjustments result in negligible improvement in the error. Thank you so much for watching. I hope you found this explanation of linear regression helpful. Feel free to leave any questions or thoughts in the comments below.